Yeah, very good morning to one and all. Welcome to the session 11 of the ATAL Faculty Development Program on Sparse signal processing and its applications. Among our Miss Professor R. Chandramurthy sir is there from IISc Bangalore. So I request Ms. Ashoda to give a brief introduction about Professor Chandramurthy sir.
Thank you, sir. It gives me immense pleasure to introduce the eminent speaker for the session, Professor Chandra R. Murthy. I welcome you, sir, on behalf of the Department of Electronics and Communication Engineering, NIT Andhra Pradesh. Dr. Professor Chandra R. Murthy, he received his BTech degree in electrical engineering from the Indian Institute of Technology, Madras, Chennai, India in 1998. His MS degree in electrical and computer engineering from Purdue University, West Lafayette in USA in 2000. In 2006, he obtained the PhD degree in electrical and computer engineering from USC San Diego. His work experience from August 2000 to August 2002, he worked on WCDMA based transceiver design and 802.11b based receivers at Qualcomm Inc. San Jose, USA. From August 2006 to August 2007, he worked on advanced receiver algorithms for the 802.16e mobile WiMAX system at BSeam Communications, now Broadcom, Bangalore, India. He has worked as an assistant professor in electrical communication engineering at Indian Institute of Science, Bangalore from 2007 to 2013, and presently he is working as an associate professor in electrical communication engineering at Indian Institute of Science, Bangalore. Now the positions he holds: he is an IEEE senior member and associate editor for the IEEE transactions on signal processing and the IEEE transactions on information theory. He is an editor for the IEEE transactions on communications. He is an elected member of the IEEE SPCOM technical community for the years 2014 to 16 and has been elected for the years 2016 to 19. He is a past chapter chair of the IEEE Signal Processing Society, Bangalore chapter. He served as an associate editor for the IEEE Signal Processing Letters during the years 2012-16. Now, the publications: Professor Murthy has got published more than 96 journal articles under his name. He has attended and presented more than 110 national and international conferences. There are 3 editorials under him. His research interest: transmit optimization, pre-coding in MIMO systems, CSI feedback schemes in MISO and MIMO systems, MIMO semi-blind channel estimation techniques, channel feedback for OFDM tracking, time-varying channels in feedback-based systems, effect of estimation errors, feedback delay and channel errors on communication systems, robust channel estimation in time division duplex systems. Thank you, sir. Now I request our expert speaker, sir, to proceed with the session. Thank you, sir.
Yeah, thank you for the kind introduction. Actually, in the research interests, compressed sensing and sparse signal processing is another major research interest, but I think that is not there from the source you picked the information from. It doesn't matter. Yeah, so maybe I share my screen now.
Yes, sir.
Just to get an idea about the background, can you just raise your hand, please, if you're a faculty, this is a faculty development program, right? So everybody is a faculty here, is what I'm assuming. Is that correct?
Yes, sir.
Okay. And I'm assuming that all participants are faculty in ECE type of departments?
Yes, sir.
Okay. Okay, very good. So, okay, so let me share my screen and I'll begin. Let me know when you're able to see my screen. And do you see the slide in full screen?
Yes, sir, you can see it, sir.
Okay, very good. So the title of my presentation today is Bayesian-inspired non-convex methods for sparse signal recovery. I was looking at the program and I saw that there have already been several sessions on sparse signal recovery. However, I also noticed that there isn't a specific session saying what is a sparse signal recovery. So I assume that that has been covered. Can I assume that people know what the sparse signal recovery problem is and some basic idea about it? Otherwise, I'll cover it anyway to some extent.
So you can take a couple of minutes to revise it, sir, because it was covered already, but just 1 or 2 minutes to just
Okay.
revise the things.
Yeah. Okay. Another thing I want to say is, please feel free to interrupt me at any time and ask questions. When I'm sharing the slide, I cannot see if you raise your hand. So instead, just directly unmute yourself. It's a small group relatively. I see about 25 participants or so. Feel free to stop and ask questions. I have a lot of slides here, but I think to me it is more important that we cover a few things that gives everybody something to take away from the talk, rather than covering a lot of material where maybe um, uh, it doesn't really help anybody so much. So especially in the initial part of the slides, because the later slides will only build up from there and go even more mathematical and so on. So especially in the initial slides, if you have any questions whatsoever, please feel free to interrupt me and let's discuss those, and then based on that we can see how far we can go with the slides. Okay, so here's the outline of the presentation. First, I will talk a little bit about this background, which will maybe be a summary of or a recap of what sparse signal recovery is and why we are interested in sparse signal recovery related problems. And then I will talk about sparse Bayesian learning, which is one of the very beautiful techniques for sparse signal recovery, and it has excellent performance and very interesting properties. And then I will go on to slightly more advanced models, which is joint sparse recovery, and talk about how one goes about, or what kind of recovery guarantees you can give for these algorithms. And then talk about some other extensions and new algorithms that are inspired by how we develop these guarantees. And then, if time permits, I'll talk about some applications of these sparse signal recovery algorithms in communication systems. Okay, so we'll start with the background and motivation and some basic results in sparse signal recovery. So this slide captures the core problem of sparse signal recovery. I don't have a pointer here, but okay, can't help it. So the basic problem of sparse signal recovery is the following. What you get to see are these observations y, which is a vector of length m. And what you would like to find out is this vector x, which is a vector of length n. And the way you get to observe this vector x is through this matrix phi, which is it's the multiplication of this matrix phi times x is what, plus noise is what gives you the vector y. This vector x is of length n, which is much bigger than, usually much bigger than m. So this is, so if I think about it as a linear system of equations, it is a linear system of, or a system of linear equations. What you have here is m equations in n unknowns. And as a consequence, we know from our basic linear algebra that if you have more unknowns than equations, you usually have infinitely many solutions. Okay, and so if the goal is to recover x from y, in fact, the goal is not very well specified because there are infinitely many solutions. In particular, if you take any one x that satisfies y equal to phi times x, then you take any x prime which lies in the null space of phi, And because phi has many more columns than rows, it has a non-trivial null space. It necessarily has a non-trivial null space, meaning that its null space, in fact, is of dimension at least n minus m. And so there is an n minus m dimensional space which contains lots and lots of vectors such that phi times x prime is equal to 0. Now, if I take any other vector x prime lying in this null space and add it to this x that I have found, then this vector x plus x prime is a new vector. But if I do phi times x plus x prime, that is the same as phi times x plus phi times x prime. And phi times x prime is 0 because x prime is in the null space of phi. And so the phi times x plus x prime is the same as phi times x, which is equal to y. So x plus x prime also explains your observations y as well as x itself does. So unless you impose some structure on this vector x, there is no way to find a unique solution to this problem of recovering x from the observations y. So y, the vector y is called measurements or observations. The matrix phi is often called the measurement matrix or also the dictionary. And the vector x is the sparse, is in fact the vector that you want to recover. And the structure that we will impose on this vector x is that it is sparse, meaning that it has only k non-zero entries, and k is much, much less than the length of this vector n. And of course, v is a noise vector. And so this is an additive noise model, which is common in most measurement systems. So the point is basically that can we use the fact that most of the entries of x are 0 to recover x uniquely given these observations y, and also you know the measurement matrix phi. So those two things are known to you, y and phi are known to you. You don't know x and you don't know v, but usually you're not trying to recover noise. You're only trying to recover the vector x. And so the noise will just remain as the residual when you, if you have an estimate x hat, you do y minus phi times x hat. That is your estimate of the residual or the noise. And you usually don't care about that. You only want to recover x. So the notation in the slide is crucial, and it's important to keep it in mind because this is the notation we'll use throughout this talk. Observations are y, they're of dimension m. The measurement matrix is phi, it is of dimension m cross n, it's a matrix. And the vector x, which we want to solve for, is of dimension n, out of which only k entries are non-zero. So, and the vector v is the noise vector, again of dimension m. So m, n, k, phi, y, and x are the notations that we need to remember. Notice that if several entries of x are 0, what it means is that one way to view matrix vector multiplication is that it is the same as multiplying columns of the matrix with entries of the vector x. So what it means is that y is obtained by taking a linear combination. In this case, only 3 entries, the colored entries, are non-zero in x. And so y is obtained as taking a linear combination of those 3 columns of this matrix phi only. The remaining columns of phi do not contribute to y. So the problem of sparse vector recovery is that of trying to identify which columns of phi have contributed to forming your vector y. Okay, so these are some different ways of looking at this problem of sparse vector recovery. So is the basic model and the key question we ask clear? Or are there any questions?
No questions, sir.
Okay. So this sparse vector recovery problem has many applications, but since I work mainly in the area of wireless communications, I show here an example of wireless channel estimation. Here you have a base station that is trying to transmit some data to a mobile user. And the signal from the base station may arrive through a line of sight direct path, and that has a delay of say tau 1. But the signal also arrives at after bouncing off a car or a building or something like that. And those arrive at delays tau 2 and tau 3. So if I look at this channel between the base station and the mobile user, I can represent it as a tapped delay line filter where there are taps at times tau 1, tau 2, tau 3, etc. So there could be a few taps in this channel. Typically, there are no more than 20 taps in a practical wireless channel. And these taps arrive with different delays, but if I look at the impulse response as a function of time, and if I'm sampling this at a fine rate because I want to capture those taps, then we see that the impulse response represented as a function of time will have only a few non-zero components, and most of the samples across time will be equal to 0. So it's naturally sparse in the lag domain. And channel estimation amounts to estimating where these non-zero taps are, that is, what are the values of tau 1, tau 2, and tau 3, and what the non-zero tap coefficients are, that is, what is the vertical height, if you're looking at the amplitude, but usually wireless channels also have a phase angle that you need to estimate. And this channel estimate is then later used in channel equalization and data detection. And it's crucial. I mean, the channel estimation is a crucial first step before you can do channel equalization, followed by data detection. So this is an example where sparsity can potentially be exploited in channel estimation, because you can exploit the fact that the channel is sparse in the lag domain to estimate the channel using far fewer number of measurements. And in the context of wireless communication, you get measurements in the form of pilot symbols that are transmitted from the base station for channel estimation. So you need far fewer number of pilot symbols in order to form accurate channel estimates. And if you go to multiple antenna channels, which is of course very hot today, multiple antennas communications, there is more structure. Specifically, channels between different pairs of antennas will often have the same support. That is, if you have signals being transmitted from two antennas from the base station, because those two antennas are relatively close to each other compared to the distance between the base station and the mobile user, the signal from the two different antennas will more or less bounce off the same structures and arrive with similar delays at the mobile user. And so tau 1, tau 2, tau 3 will be common across different pairs of antennas. And also typically multipath occur in clusters. So if there is a building, it will not reflect only a single path of the signal, but rather form a cluster of multipath at the receiver. And the channels between different pairs of antennas could be correlated. So there are inter-antenna correlations. And one would like to develop sparse signal recovery algorithms that exploit all such structure. Okay, now coming back to the problem of compressed sensing or sparse signal recovery, it deals with three main questions. The first question, which I will not be talking about in this presentation, is how to design these sensing matrices, the matrix phi that I showed you in a previous slide. So the question is, how do you design this matrix phi such that you can recover sparse vectors accurately? What I showed you in the previous slide is actually a simplified version of the problem where the vector x itself is sparse. In practice, x need not be sparse by itself, but x could be sparse in some other domain. So there was an earlier talk about the FFT and sparsity through the FFT. So similarly, you could have other basis functions. So for example, if you have an image, so if x represents the pixel values across an image, then under a discrete cosine transform, you can show that the most images can be represented as sparse vectors. That is, if you take an image, the pixel values across an image, and you take its discrete cosine transform, and you look at the vector that you got, the vector will have a small number, let's say 1% or 2% of the values will be significant, and most of the entries will be close to 0. And in fact, if you zero out those entries that are small, and then you take the inverse discrete cosine transform and you look at the image, it will be of transparent quality. That is, our human eye will not be able to make out the difference between the original image and the image where the small coefficients in the DCT domain have been zeroed out. So X need not be sparse in this is called the canonical basis. It could be sparse in some other basis. So if that basis is represented by the matrix psi, which is of size n cross n, that is often called the sparsifying basis. Then you want to design a matrix A such that A times psi forms your overall sensing matrix. And you want to design this matrix A such that you can recover sparse vectors accurately. For example, if you have this matrix phi, which has two columns which are equal, then if the column corresponding to one of them has a non-zero coefficient associated with it, there is no way you will be able to figure out whether it is column 1 that has given rise to the output, or column 2 which has given rise to an output, if columns 1 and 2 are the same. The same applies if columns 1 and 2 are highly correlated with each other. If columns 1 and 2 are highly correlated with each other, then either of the two columns could explain your observations, and you won't be able to distinguish which column has actually contributed to the observations. And so you want to design these matrices in such a way that it allows you to recover sparse vectors with high accuracy. And the second important aspect is guarantees for recovery. That is, under what conditions can we be assured that this measurement matrix phi will allow us to recover sparse vectors with a high degree of accuracy. The third aspect is to develop computationally efficient algorithms for recovering this sparse vector X. And so in this talk, I'll primarily focus on guarantees for sparse signal recovery. Just excuse me for a second. I need to press hide here. Okay, that's better. Now we go back to the slides. Okay. So in this talk, I'll focus on new algorithms and guarantees for sparse signal recovery. Okay, so before I talk more about the compressed sensing problem, I want to mention two other applications where compressed sensing ideas are also very useful. The first is in what is called robust linear regression. So linear regression again refers to the fact of finding these coefficients of this vector x such that you can explain your observations y. And in many linear regression problems, you typically assume that the noise is what we call white, but basically it is isotropic. That is, it doesn't have a few directions in which you have a large noise and other components have small noise. However, in practice, your noise could have outliers. So what is shown here is this V can be written as the sum of Vs and Vg, and Vs has some outliers. It has two large components, but most of the other components are zero, whereas it has another component Vg, which is a Gaussian noise, and those components are all similar in magnitude to each other. In this case, it is known that any typical linear regression algorithm can be thrown off very easily by introducing a small number of outliers. In the context, for example, of multi-sensor data, where the vector y is obtained by taking measurements from m different sensors, if a small number of these sensors are malfunctioning, and then you can model their observations as the true measurement plus some large noise, then the small number of outliers can really throw off typical linear regression algorithms. And so sparsity can also be used to solve these kinds of linear regression algorithms where you have outliers in your noise. The way to do that is to transform the signal into an overcomplete problem. Overcomplete problem simply means that you have a measurement matrix with more number of columns than rows. And the way to do that is to write y as some phi times x plus identity matrix. So psi is equal to the identity matrix times this Vs plus this Gaussian noise Vg. So it's the same model as before. So y equal to phi x plus v, but I'm writing it explicitly as writing v explicitly as Vs plus Vg, and I'm associating the identity matrix as an observation matrix with this vector Vs. And then I can concatenate this Vs and x together and write it as phi psi concatenated with each other horizontally times a bigger vector x vs plus vg. Now, because this vs has only a few non-zero components corresponding to the outliers, vs is also a sparse vector. So x vs together, if x is a sparse vector and vs is a sparse vector, x vs together is in fact a longer or a bigger length sparse vector. And so you can now directly use sparse recovery algorithms with the new measurement matrix phi psi concatenated with each other. Another example is also in robust linear regression, but for the overdetermined case. So you have again a matrix A, which is of size m by n, but here m is much bigger than n, and the goal is to solve for x. However, you have your measurements y are corrupted by these outliers represented by the vector capital E, which is again a sparse vector. So you have a very large number of measurements. And normally you should be able to recover X by using standard linear regression techniques like principal component analysis. But these techniques will fail miserably if you have these kinds of outliers. So one way to tackle the problem is to perform a singular value decomposition on A. What that does is to write A as U1 sigma V1 transpose. And this is called the economy SVD, or the it's called the economy singular value decomposition of the matrix A. And this U will then be of size n cross n, and sigma will be of a matrix of size n cross n, and V1 transpose will also be of size n cross n. Sorry, U1 will be of size m cross n. Sigma will be of size n cross n, and V1 transpose will also be of size n cross n. Then the orthogonal complement of this U1 is represented by U2, and that is of size m minus n cross n, and it has the property that U2 transpose times A is the all-zero matrix. So then if you pre-multiply your Y by this U2 transpose, you see that what you get is U2 transpose times A times X plus U2 transpose times capital E plus U2 transpose times small e. But U2 transpose A equals 0, so basically your process measurements will look like U2 transpose capital E plus U2 transpose times small e. Now we can directly apply sparse signal recovery techniques with U2 transpose as the measurement matrix to first recover E. Once we've recovered E, we can subtract E from Y. Then you are back to a Y equal to AX plus small e type of model, where the goal is linear regression, and you can recover X from that. So again, a sparse signal recovery can be useful for robust linear regression in the overdetermined case when your observations are corrupted by sparse outliers. So this is the fundamental problem of sparse signal recovery. In the noiseless case, that is when V is equal to 0, the goal is to solve for the vector X with the smallest possible L0 norm. So L0 norm is something that simply counts the number of non-zero entries in a vector. So if I take a vector like 1, 2, 3, 4, 5, its L0 norm is 5 because there are 5 entries and all 5 are non-zero. If I have a vector like 2, 3, 4, 0, 0, 0, 0, 0, 0, 1, then the L0 norm of that vector is 4 because there are 4 non-zero entries. And you want to find the vector which has as few non-zero entries as possible, which also satisfies y equal to phi times x. In the noisy case, you may allow yourself a certain margin for error, and instead of requiring that y must be equal to phi times x, you allow this margin of error and say y minus phi x, the L2 norm or the Euclidean norm, which is the square root of the sum of the squares of the entries of the vector, should be at most equal to beta, some upper limit beta. And this upper limit beta comes from your guess of what the noise standard deviation is. And this problem is often called the L0 minimization problem because it's trying to minimize the L0 norm. Incidentally, the L0 norm is not a norm. It doesn't satisfy, for example, the homogeneity property which all norms need to satisfy. But nonetheless, in the literature, it still goes by the name of L0 norm with the understanding that it's actually not a norm. This L0 norm minimization problem is of combinatorial complexity, and also it's not robust to noise. So a little bit of noise added to phi times x can dramatically change the L0 norm minimizing solution that you can find. It's combinatorial complexity because when you think about it, if you want to find the x with as few non-zero entries as possible that solves y equal to phi x, the way to solve for it is to first see whether it's possible to find a vector x with just one entry non-zero, which explains your observations y. So in that case, you will see if y can be written as, for example, a scaled version of the first column of phi. If that's not possible, you will see whether y can be written as a scaled version of the second column of phi, and so on. And once you tried all n columns and you found that none of the n columns is directly collinear or linearly dependent with y, what you do is you ask if it's possible to take a combination of two entries of x. That is, can y be written as a linear combination of two columns of phi? So you would take columns 1, 2, 1, 3, 1, 4 up to 1n, and then 2, 3, 2, 4 up to 2n, and then 3, 1, 3, 3, 3, 4, 3, 5 up to 3n, and so on. So there are n choose 2 pairs of columns that you can choose. For each n choose 2 pair of columns, you ask whether y can be written as a linear combination of those two columns of phi. If that's not possible for any pair of columns, you try triplets of columns. You take 3 columns at a time and see if you can explain y using those 3 columns. And you have to keep going like this till you find the first subset of columns, or the smallest subset of columns that you need to take, such that you can find a solution to y equal to phi times x. And that is why the problem is of combinatorial complexity. And it turns out that this problem can actually be related to the problem of some very famous problems related to graph coloring in the computer science literature, which are known to be what is called NP hard, non-polynomial hard. And so because they are NP hard, it means that you will not be able to find an algorithm which scales well with the problem dimensions. So in other words, as I scale the number of measurements and the number of entries in the vector x, the problem will get exponentially harder and harder to solve. And you don't really want to solve this L0 norm problem because of, even for problems of reasonable size. So for example, even if you want to find a 10 sparse solution, that is there are 10 non-zero entries in the vector x for a vector of length 100, let's say. So a 10 sparse solution to a 100 length vector using observations y equal to phi x, where y could have, let's say, 20 or 30 dimensional, be a 20 or 30 dimensional vector, then the complexity in solving for this will be of order 100 choose 10, which is enormous. And so it's very difficult to solve this problem as stated. So in fact, maybe 30 years ago, this was the state of the art. People were interested in finding sparse solutions, but then they realized that the problem is actually combinatorially complex and it's not robust to noise, and so it was not very interesting to solve. However, there were a few breakthroughs in the area of compressed sensing that made this problem much more solvable. So one solution, one such breakthrough was through this thing called the null space property. So here we are putting restrictions on phi in addition to restrictions on x. The measurement matrix, okay, if its null space does not contain any sparse vectors, then it turns out that this problem y equal to phi x will have a unique sparsest solution. So that brings me to another point, which is that first of all, I started out by saying that y equal to phi x, it is a system of linear equations with the number of measurements being less than the number of variables. And so typically it has infinitely many solutions. And so finding the sparsest solution is is one way to impose structure on X that can potentially lead to unique solutions. But what if Y equal to phi X had multiple sparse solutions? In that case, you have no way of choosing which of those sparse solutions you are most interested in. And so the very first question we need to answer is, under what conditions will Y equal to phi X not have multiple sparse solutions? And the answer is that if it will have a unique solution, that is, it won't have multiple sparse solutions if the null space of phi does not contain any sparse vectors. And in particular, for the recovery of all vectors of sparsity level k, it is necessary and sufficient that you have at least 2k number of measurements. And in fact, for a given x, a unique solution is guaranteed with high probability if m is just greater than or equal to k plus 1. So the last bullet actually makes sense if you think about it in the following way. Suppose the vector x was one sparse. How many equations do you need to recover the vector x? It turns out you only need two equations. You need one equation, sort of. I mean, the degrees of freedom in x is that it has one non-zero entry, and second, you don't know what the location of the non-zero entry is. And so you need two equations, one to tell you where the non-zero entry is located, and one to tell you what the value of that non-zero entry is. Similarly, if you have a vector x, which is say 10 sparse, then you need 10 equations to tell you where the non-zero entries are. But it turns out you need only one more equation. That is, you need a total of only 11 equations to tell you which combination of 10 entries of x are non-zero. So the upshot of all this is that you're able to compress this vector x and still go back to the vector x. You know that there is a unique solution. All you have to do is to figure out how to solve y equal to phi x for the sparsest possible solution. This is possible if we restrict ourselves to sparse signals and we sample in an appropriate basis phi. So for instance, if the vector x itself is sparse, you can't have the matrix phi also to be sparse. If phi and x are both sparse, it makes it hard to recover x from y. That is because for example, if the matrix phi is sparse, it has lots of zeros in it. And so say, for example, let's say the sixth column of phi has only zeros in it. Then if the sixth entry of x is non-zero, it will only multiply 0 when you get all the entries of y. And so you have no way of knowing whether the sixth entry of x is 0 or non-zero. So if you choose your basis in which you're sampling the vector x appropriately, then it is possible to have a unique recovery of this sparse vectors from y equal to phi times x. Another very important breakthrough was in terms of the relaxation. So we already saw that the L0 minimization problem is an NP-hard problem. It's computationally too expensive to solve. So instead of solving the L0 minimization problem, if we consider the following problem, minimize the L1 norm of x subject to y equal to phi times x. What is the L1 norm of a vector? It's simply the sum of the magnitudes or modulus value of all the entries of x. So for example, if I have a vector with entries 3, -5, and 2, then the L1 norm of that vector is 3 plus 5 plus 2, which is 10. So minimize the L1 norm of x subject to this constraint y equal to phi x. Now this problem, this L1 norm of x is actually a convex cost function, and the constraint set y equal to phi x is actually a convex set. Specifically, if you find two different solutions to y equal to phi x, then any point on the line connecting these two solutions will also satisfy y equal to phi times x. So this is a convex cost function L1 norm of x subject to a convex constraint, which is y equal to phi times x. So overall, this is a convex optimization problem. Yeah, so any optimization problem is said to be convex if the objective function is a convex function of its argument, and the constraint set is convex. That is, if you take any 2 points in the constraint set and you draw a line connecting those 2 points, that line must also lie inside that convex set. So it's a convex cost function with convex constraints, and so it's a convex optimization problem. And in fact, it can be posed as what is called a linear program. And this allows one to develop computationally efficient algorithms to solve for X. However, we are not solving the L0 minimization problem. So we should ask the question of, is this approach going to work? Will it give us the L0 minimizing solution? Turns out the answer is yes. It will, under certain conditions, it will give the same solution as L0 minimization. And what are those conditions? The first condition is that the measurement matrix must be random. That is, the entries of phi must be chosen from a random distribution. You cannot use a structured measurement matrix. And second point is that you will have to use a slightly larger number of measurements. So the order of measurements is of the order k times log n over k. In the previous slide, we saw that m to be of the order k plus 1 or 2k is sufficient. But here we see that you need m to be of the order k times log n over k, which is still much less than capital N, which would be the number of measurements needed if you had no structure in this vector x. And also this use of the L1 minimization turns out is robust to measurement noise, meaning that if noise perturbs your observations y, you get y equal to phi x plus v, and v is a noise vector, then the presence of the solution you get in the presence of v is going to be close to the solution you get even if v was not present. So that is a very desirable property in any recovery algorithm, which is that a small amount of noise should not dramatically affect your solution. Okay, so and solving it via this convex optimization problem gives you those kinds of guarantees that it is robust to measurement noise. I'll talk more about that in a bit. The third breakthrough is that these algorithms, like for example the problem of L1 minimization, they can actually come with recovery guarantees. What do I mean by that? I mean a result of the form that is shown at the bottom of the slide, which says that if you were to solve this problem P1 eta, which is to minimize the L1 norm of Z, subject to phi Z minus Y, L2 norm is less than or equal to eta. So the eta is again your error margin. You're allowing a small error between phi Z and Y. And this problem, when you solve this problem, you will get a solution X star which satisfies the equation at the bottom of the slide, meaning that the L1 norm of the difference between X and X star, which is the L1 norm of the error in recovery, is at most some coefficient. In this case, it's written as 2 times 1 plus rho over 1 minus rho, times the error in approximating X by a k-sparse vector. So in particular, if X is already a k-sparse vector, then this quantity sigma k x L1 will be equal to 0. So it is some coefficient times the error in approximating X by a k-sparse vector, plus another coefficient times the noise variance, or the bound on the noise that we imposed. And these kinds of recovery guarantees are what made compressed sensing very, very popular, because you're not only giving good algorithms for recovering sparse vectors, you're also able to characterize exactly how good these algorithms are and what kind of sparse vectors can be recovered using these algorithms. Now, yeah. So in this case, the property that we used is what is called the robust null space property, which is written mathematically here, but maybe for the moment I won't go into the detail of what this RNSP is and what it means, etc., unless there are specific questions from people who are interested to know about it. But suffice to say for the moment that phi is a measurement matrix which satisfies this property called RNSP of order k. Okay, now I'll give you one more example of the kind of recovery guarantees one can give, which is based on what is called the restricted isometry property. We say that a matrix A satisfies a restricted isometric property of order k if there exists a constant delta between 0 and 1. So if delta exceeds 1, that doesn't count. I mean, we don't want that kind of deltas. But if there exists a constant delta k, which belongs to the interval 0 to 1, such that 1 minus phi k times the L2 norm of z squared is less than or equal to the L2 norm of az squared, which is in turn less than or equal to 1 plus delta k times L2 norm of z squared. So this is called an isometry property because it preserves length. So you see that the length of az is going to be similar to the length of z, provided delta k is small enough. Then multiplying a with z doesn't change the norm of z. Okay. And the smallest delta k for which this actually happens is called the kth restricted isometric constant of this matrix A. So here is a theorem. What it says is that suppose the 2kth restricted isometric constant of phi satisfies delta 2k is less than some number like 0.6246. There are many other similar results that are available out there. Then for any x and y with ax minus y L2 norm less than or equal to some constant eta, then the solution to the L1 minimization problem, minimize the L1 norm of z subject to phi z minus y is less than or equal to eta, satisfies that this the L1 norm of x, the difference between x and x star. So the L1 norm of the error in recovering x is at most some constant c times the error in approximating x by a k-dimensional or a vector with k non-zero components times the L1 norm of the error in approximating x by a vector which has k exactly k non-zero or at most k non-zero components plus some other coefficient d times square root of k times eta. So it depends on how much noise you've added. If eta is large, then the bound becomes loose. If eta is small, then the bound becomes tighter.
Sir, excuse me.
Yeah.
Sir, in the previous slide in restricted isometry property, sir, can you go to the slide, sir, 1 second? Sir, it resembles some kind of a frame bound or something like that, sir.
Yeah. So it is in fact that. Yeah.
Sir, what is that del k, sir? What is why we are very particular that the value should take between 0 and 1?
Well, see, one thing is that delta k being negative doesn't make sense here at all, because we are saying 1 minus delta k times L2 norm of z squared is less than or equal to norm of az squared less than or equal to 1 plus delta k times. The direction of the inequalities, I mean, the first and last inequalities will not hold if delta k is negative, right? Because 1 minus delta k times L2 norm of z squared will not be less than or equal to 1 plus delta k times L2 norm of z squared if delta k is negative. So the negative numbers can be thrown away directly like that. If delta k is more than 1, you can see that the lower bound is useless because it's saying that norm of az, L2 norm of az squared should be greater than or equal to some negative number. Of course, L2 norm of az squared is the norm squared of a vector. And so that will always be non-negative. And so saying that it should be greater than or equal to some negative number doesn't add any value to this property. And also delta k being close to 0 means that the lengths of sparse vectors is more or less preserved. So we would like matrices which have delta k as close to 0 as possible.
Thank you very much, sir. Thank you.
The fourth breakthrough, also equally important, is that these recovery guarantees led to a whole slew of different recovery algorithms being proposed for sparse signal recovery. And here are three of the very popular classes of algorithms. The first is a set of greedy algorithms, which include things like matching pursuit, orthogonal matching pursuit, cosamp, etc. I won't read out names of every algorithm that's available out there, but most papers in the literature often focus on this orthogonal matching pursuit and basis pursuit because they're very simple algorithms and you can get ready-made MATLAB code for these algorithms. And so many papers consider these algorithms because they're easy to implement. But there are many others which are also based on. So the first class of algorithms are greedy algorithms, which basically try to identify one column that must belong to the support set and then somehow remove the effect of that column on the observations, try to find one more column that explains your observations and so on. Whereas the second class of algorithms are relaxation-based algorithms, where you minimize some form of a diversity measure. A diversity measure is one that somehow counts how many non-zero entries your vector X has. And you want to minimize that kind of a diversity measure, but instead of minimizing the L0 norm, you do something like minimizing the L1 norm, which can then be cast as a convex optimization problem. And so there are several algorithms that sort of try to use this approach. And the third method is a iterative method where you use a thresholding algorithm which recovers the sparse vector and then thresholds them to some small value and sets the entries of the vector below that small value to 0 and then tries to recompute the estimates. And there are methods like iterative hard thresholding and hard thresholding pursuit in this class of methods. Okay, so we've discussed 4 breakthroughs in compressed sensing, which kind of motivates why we are interested in this area. It's because one, through null space property, you can guarantee unique recovery of sparse vectors, and 2, if you, instead of solving the L0 minimization problem, if you solve the L1 minimization problem, you can often end up with the same solution as the L0 minimization problem, provided some conditions are satisfied. The third breakthrough is in terms of a variety of recovery guarantees that you can give for these algorithms. And the fourth is a whole slew of recovery algorithms that have been developed in the literature, making it easy to come up with the use of sparse signal recovery to solve problems in other fields. Okay, so these are the different recovery methods. And all these methods come with recovery guarantees. And there's a very nice, very nice book by Rauhut and Foucault that you can download for free from the internet. And it's called, I think, A Mathematical Introduction to Compressed Sensing or something like that. But this is a very comprehensive book which has lots of good results and it's also very well written. And so one can find guarantees for many of these algorithms in this textbook. However, is there another question? Okay, so this is not the end of the story. The performance of these algorithms, basis pursuit and orthogonal matching pursuit, and the other algorithms I presented in my previous slide are dependent on the measurement matrix Phi. And you often end up with poor performance when those conditions are violated. Another issue is that it's hard to relate the estimation error to the dictionary or to the sparse vector that you're trying to estimate. And further, when you have a dictionary with highly correlated columns, that disrupts the L0, L1 equivalence, making it harder to analyze the performance of these algorithms. For the basis pursuit algorithm, what you can show is that the performance does not depend on the non-zero coefficients of the sparse vector. It only depends on how many entries of the sparse vector are independent. However, orthogonal matching pursuit, on the other hand, the performance is highly sensitive to the magnitudes of the non-zero coefficients, and you can end up with poor performance if you have unit magnitude coefficients. Other issues are, for example, embedding, if you have a measurement matrix which has some embedded parameters that are unknown to you, how do you do joint estimation of those embedded parameters and the sparse vector? And also exploiting structure when it is available. So all these can lead to important performance improvements of these sparse signal recovery techniques. Okay, so to just recap what we've seen so far, we've seen the basic problem of sparse signal recovery, and we've discussed some key breakthroughs in compressed sensing that has made this area very popular. We also discussed about a few algorithms and guarantees. So, however, it has several limitations. So, as I mentioned earlier, they have the issue of scaling or shrinkage of the recovered sparse vector. So, it's like a bias that gets added to the sparse vector because you're trying to find the sparsest solution. And it also does not cover the case of correlated dictionaries. And finally, if your measurement matrix has some embedded parameters, then you'll need to estimate those embedded parameters as well, in addition to doing data detection, in addition to recovering the sparse vector. Okay, so then we come to part 2, which is to talk about non-convex methods. Okay, are there any questions at this time? Okay, if there are no questions, then yeah.
Sir,
Yes.
if the signal is by nature, if it is not in the sparse, then how to know in which transform domain it is having sparse nature, sir?
So that problem is called the problem of dictionary learning. I'm not covering that in this tutorial, but there are methods. So in particular, if you're given only one measurement of a vector, or you have one set of measurements, you get y equal to phi times x with or without noise. And if you don't know in which phi this vector x is sparse, you cannot recover both phi and x from this vector y. You will need multiple, in fact, lots of measurements in order to recover both y and the dictionary in which the vectors x are sparse. But if you have that, if you have multiple measurements, then you can potentially try to estimate both the sparsifying dictionary and the sparse set of sparse vectors.
Okay, sir.
In some particular scenarios, for example, I gave the example of an image which is sparse in the DCT domain. So if you choose the DCT matrix as your sparsifying basis, then you can recover, you can use sparse signal recovery algorithms to recover images from compressed images.
Yes, sir. Sir, ECG signal in which domain it can be sparse, sir?
I don't know.
Okay.
Yeah.
Thanks.
Yeah, I don't know, but I think if you look at some papers on ECG, you will probably find they probably discuss in which domain the ECG signal will be sparse. But one thing is that none of these sparse signal recovery algorithms will work if you don't know what the measurement matrix is. And the measurement matrix has the sparsifying dictionary hidden inside it. So like I mentioned here, it's of this structure here. So the actual overall sensing matrix is a matrix A, which is your actual sensing matrix, times this matrix psi, which is the sparsifying basis. So if you don't know psi, even if you knew what your sensing matrix A is, you will not be able to compute phi. You cannot do any sparse recovery algorithm. So all these sparse signal recovery algorithms assume that you've used some technique to figure out what the psi is, which is the sparsifying basis.
Sir, you told that with multiple measurements we can with multiple measurements we can able to assess this measurement matrix. So what
sparsifying basis?
Sparsifying basis, sir. So what method will help us to assess this sparse traces with multiple measures?
There are very, very large number of techniques, and all of these go under the name of what is called dictionary learning.
Okay, sir.
So if you Google dictionary learning, you will get lots of papers on this. Perhaps the most famous method in this class of method is what is called the KSVD method.
Okay, sir.
It's called the KSVD.
Okay, sir.
But there are many, many other methods.
Okay, sir. Thank you, sir.
The dictionary learning is an area of research by itself. A lot one can talk about how to learn the dictionary. Yeah, I have some references at the end. Maybe I can point you to some papers on dictionary learning, which talk about how to recover both the dictionary and the sparse vectors.
Sir, excuse me, sir.
Yeah.
The recovery guarantee, while the recovery can is there any problem in del K? Whether we can able to find out the del K?
Can you repeat your question? I think part of it got lost. Now again, yeah, please go ahead. Can you tell your question again?
Is some of the literature saying that the del K is NP hard?
Finding del K is NP hard. That is correct. I didn't talk about it, but you are right.
Okay.
So
So
finding del K is actually an NP hard problem. And so, in fact, given a matrix A, you don't know what its delta K is. And if you want to find its delta K, that by itself is an NP hard problem. And if you don't know whether your matrix satisfies this restricted isometry property, then how will you give guarantees on recovery, right?
okay. So if the del K we cannot able to find it is an NP hard, then in what way can we able to find out the bounds?
Correct. So if you can't find the bounds, or if you can't show that the matrix satisfies this restricted isometry property, then you have no way of verifying that the matrix will be a good matrix for sparse vector recovery. There are two answers to this question. The first answer is that what one can show is that if your measurement matrix A has random entries, not deterministic. So for example, you choose the entries of A from a Gaussian distribution. Then you can show that with high probability, in fact, with what is called overwhelming probability, meaning that the probability that the matrix does not satisfy this condition written here in this inequality written here. The probability that the matrix A does not satisfy that inequality or this condition it will go to zero exponentially fast in the size of this matrix. And so then in that case, what it means is that you simply choose a matrix from a random distribution. So for example, you choose the entries of A to be plus or minus 1 with equal probability. Okay, then you have a measurement matrix which has roughly half plus ones and half minus ones. And that matrix will satisfy the restricted isometry property with a certain, you can choose the constant, and that decides the size of the matrix you should be choosing. And if you choose the constant, let's say you've chosen the constant to be delta K equal to 0.3 is what you're targeting, that fixes this the number of rows in this matrix A that you need to choose. If you choose at least that many rows in the measurement matrix A, then it will satisfy this kind of a condition with extremely high probability. So that is one way to do it. Another thing is that the second part of my answer is that this restricted isometry property is what we call a sufficient condition for recovery. So if I go to the next slide, you see it says, suppose the 2kth restricted isometry constant of phi satisfies delta 2k is less than 0.62. Then you are guaranteed that you will recover sparse vectors from these low dimensional measurements. It does not say that if the matrix phi does not satisfy this 2kth restricted isometry constant condition, then your recovery will fail. So it's the same. What I'm trying to say is if statement A or condition A implies condition B, it's not the same as saying that A complement implies B complement. Of course, it's true that B complement implies A complement, but it's not true that B complement implies, A complement implies B complement. So it's a sufficient condition. If the matrix phi satisfies this 2kth restricted isometry property, then you're guaranteed that you will recover. But if it does not satisfy the restricted isometry property, you are not guaranteed that you will fail. You may still succeed. And in fact, in practice, many of these algorithms succeed for many different types of measurement matrices for which you don't know whether it satisfies this 2kth restricted isometry constant or not. So when you're faced with a practical problem, you can actually just try these sparse recovery algorithms. And if they work, it means that, yeah, whether your matrix satisfies it or not is not relevant. It's what matters is your algorithm works and you're able to recover those sparse vectors accurately.
Okay, so if it satisfies this del 2k, then that is enough. Or if we can able to recover it, if the performance of recovery is good, then no need to consider about the bounds.
Yeah, exactly. You don't need to worry about the bounds. It works in practice. So you have a method that works. The restricted isometry property only is only needed if you want to give guarantees like this. Because this is one way people know how to give guarantees for the recovery of sparse vectors. There are other approaches also. There are guarantees you can give based on what is called the mutual coherence property of the matrix. But all of those are again still sufficient conditions for recovering sparse vectors. In other words, if those properties are satisfied, if the mutual coherence is small enough, then you're guaranteed that sparse vectors are recoverable from the measurements. But if the mutual coherence property fails, then it doesn't mean that your recovery will also fail. Your recovery may still be successful.
Okay. 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 Thank you.
Any other questions?
Sensing matrix.
How do we generate the sensing matrix? Yeah, so as I mentioned, in many practical situations, the measurement matrix is given to you. It's decided by nature. So, for instance, if you're taking, there is this thing called the single pixel camera. So they build a specific hardware which incorporate a measurement matrix into the hardware. So that way you can acquire compressed images directly rather than acquiring a full complexity image and then running some compression algorithm like Lepel-Ziv compression or something to compress the image. You can directly acquire a compressed image using these single pixel cameras. And they use some specialized hardware, and that specialized hardware specifies the sensing matrix. And you need to know what that specialized hardware is doing while it's acquiring the image, because you need to know what phi is in order to recover the image back from the measurements y. So in wireless communication applications, oftentimes the sensing matrix is decided by the kind of pilot signals you use. So for instance, if you use pilot signals that are plus or minus 1 with equal probability, then and you construct a measurement matrix out of that, then it's a measurement matrix that is known to you, but which has random entries. And you can use such measurement matrices for recovering sparse vectors or doing channel estimation.
So then how can we test whether the matrix is satisfying the property, restricted isometric property? We randomly generate only plus or minus 1 the matrix. Then how can we check that is?
So like I said, you cannot check it. Checking whether a matrix satisfies the restricted isometry property is itself an NP-hard problem. So there's no hope of actually checking whether the matrix satisfies the restricted isometry property or not. The guarantee you can give is that if your measurement matrix is random, okay, then with very high probability, it's going to satisfy this restricted isometry property. Of course, when you generate a random matrix, you may be unlucky, and you may have generated that one bad matrix that won't satisfy the restricted isometry property. But that is something that will happen with extremely low probability. And in fact, you can choose the probability with which that will happen. You can make it as small as you wish. So you can choose a limit like 10 to the minus 10 and say that I'll generate my measurement matrix randomly. I want the probability that this measurement matrix does not satisfy the restricted isometry property to be smaller than 10 to the minus 10. Then when you generate a matrix at random, you don't know whether it will satisfy the restricted isometry property, but you know that with extremely high probability it will. And then you can try to use that matrix and recover your sparse vectors. If you find that you're failing, then maybe you were unlucky and you chose that one or that very rare matrix that does not that happens to fail this restricted isometry property. And like I also mentioned, still this restricted isometry property is a sufficient condition. It's actually not necessary for the success of these algorithms. Algorithms may work well even if the property is not satisfied. Okay, so before I go into this part 2, let's see, we are at 12:45. Maybe I'll take a 2-minute break, just so that all of you can also just move around a bit. I think 2 hours at a stretch is too much for everybody. So let's take a 2-minute break, or if you prefer a longer break, you tell me. But let's take a very short break. I think it will be too heavy if we go continuously for 2 hours. So
yes, sir. Let's go for 2 minutes.
2 minutes break. Okay.
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 Not now at 1:30.
So maybe we continue. Is it all right?
Yes, sir. Let's continue.
Okay. So now let's go to a different class of techniques. I mentioned to you that there are limitations. That is, these kinds of algorithms, their performance depends on the structure of this measurement matrix, and they can have poor performance when those conditions are violated, like when the restricted isometry property is not satisfied, although it is only a sufficient condition, not necessary, but still it's possible that you'll end up with poor performance when these conditions are violated. And the other thing is that it's hard to relate the estimation error to the dictionary. That is, if you see these guarantees that I showed you, they're of this form, where the error in recovery is being upper bounded by the error in approximating x by a k-sparse vector plus the amount of noise that is added. That is this eta thing. But notice that on the right hand side, there's no property of phi that is coming into the picture. So if you use one particular phi versus a different phi, it makes no difference to the upper bound. So it's hard to understand how well a given phi matrix will perform in terms of sparse vector recovery. The entire dependence on phi is captured, it has been sort of captured into this restricted isometric constant property. Okay, it's as long as phi has this 2kth restricted isometric constant less than 0.6246, the result at the bottom of the slide is valid. So often, however, we would like to have some insight into how the estimation error depends on this matrix phi. And if the measurement matrix phi has correlated columns, then again, many of these algorithms can fail. And there are other issues like estimating embedded parameters and so on. So to overcome some of these, one can look at non-convex methods. So there are basically two classes of methods here, and they're called type 1 methods and type 2 methods. In type 1 methods, what you do is to impose a prior on this vector x you're trying to recover. That is, you say that the vector x comes from a certain distribution. Now, in reality, it may not come from that distribution, but you impose this kind of a prior structure on x in order to come up with an optimization problem, which hopefully will give you sparse solutions. And in fact, L1 minimization, which is this basis pursuit or lasso algorithm, is a special case of these types of methods. L1 minimization is equivalent to imposing what is called a Laplace prior on these sparse vectors. Another class of methods are hierarchical Bayesian methods, which are called type 2 methods, where you not only impose a prior on x, you also impose a prior on the parameters of the distribution on x. And that leads to iterative reweighted methods, and in particular, this method called sparse Bayesian learning, which I'll be discussing in more detail in the coming slides. And there are faster versions of these algorithms, including approximate message passing. So to explain the first type of methods, that is type 1 method, in maximum a posteriori probability estimation, your goal is to recover this vector x. I really wish I had a pointer and my mouse isn't working. Oh well. So map estimation, the map estimation problem is exactly this equation in the box here. You define your estimate to be the value of x that maximizes the probability density function of x given your observations y. Now, if you simply use Bayes' rule, p of x given y is equal to p y given x times p of x divided by p of y. And maximizing px given y is the same as maximizing the log of px given y, because the logarithm is a monotonic function, which is the same as minimizing the negative log of px given y. And px given y, as I mentioned, is p y given x times p of x divided by p of y. But p of y does not depend on x at all. So it's irrelevant for this optimization problem. So dropping that term, you can write this map estimation problem as the problem of finding the x that minimizes the negative log of py given x minus the log of p of x. Now, the thing that is under your control here is this p of x. You can choose what kind of prior you'll impose on x. If you use different types of priors, you will get different algorithms with different associated performance complexity trade-offs. Py given x, typically, if you know what x is, y is equal to phi x plus noise. And so if you're given x, the py given x is simply the density of the noise shifted by this vector phi times x. And often we assume that the noise is Gaussian. So in that case, py given x is just a Gaussian random or Gaussian PDF with mean equal to phi x. And so the log of py given x, or the negative log of py given x, is nothing but the L2 norm square of y minus phi times x, which is the first term in the third line. The second term, like I mentioned, p of x is what's under your control, and x is a vector of length n. And so p of x, typically, if you think of the entries as being independent of each other, then you can write p of x as the product of the density of the individual entries of x. When you take the log, this becomes the sum of the log of the density of the individual entries in x. And so that is written as summation I going from 1 to n, g of xi. And typically you assume that this density of x is symmetric about 0, so it's written as g of mod xi. This lambda factor simply accounts for the trade-off or the importance you want to give to the first term and the second term. If lambda is very large, it will only try to minimize the second term because the first term doesn't matter much to the minimization. If lambda is very small, you're giving the prior very little weight and you're focusing on trying to make y to be equal to phi x. In order to, what one can show, which I'm not showing here, is that if you want to get sparse solutions, you need to choose this g of x to be a concave non-decreasing function of x. In particular, if I choose g of x to be mod of x, then mod of x is both concave and convex, so it actually satisfies this property that it's a concave non-decreasing function of x. What is a concave function? It's a function that looks like log x or square root of x and so on. It curves downwards. A convex function is a function like e power x, etc., which curves upwards. So if you want sparse solutions, g of x should be a concave non-decreasing function of x. And examples are like g of x equals mod x raised to the power p, where p is any number which is less than or equal to 1. And if it satisfies these properties, that is, its g of x is a concave non-decreasing function of x, then you can show that any minimizer of this map estimation problem will have at most m non-zero entries. So you're guaranteed to get sparse solutions. Typically, you're interested in much more much sparser solutions. You don't want to get solutions which have m non-zero entries. You want solutions which have only k non-zero entries. But at least we can guarantee that all the local minima of this cost function, and therefore the global minimum of this cost function, will never have more than m non-zero entries. So the optimization problem that we need to solve is then to minimize this capital G of x, which is the L2 norm squared of y minus phi x plus some lambda times the summation of g of mod xi. Now we saw that g of x is a concave monotonically increasing function in x. Y minus phi x L2 norm square is a quadratic function in x. And so the first term is actually a convex function of x. The second term is actually a concave function of x. And so overall, this capital G of x is the sum of a convex function plus a concave function. This kind of convex plus concave function minimization is typically not easy to solve. Okay, but there are many different options you can choose for g of x, and like we said, for example, g of x equals mod x raised to the power p is something that will promote sparsity. Another example, I have other examples in later slides, but another example could be g of x equals log of mod x plus some small epsilon, just to make sure that x doesn't x going to 0 doesn't make the cost function minus infinity. But g of x equals mod x plus epsilon, that also promotes sparsity, etc. And for any given choice of g of x, there are many options for solving this optimization problem. Usually, if an optimization problem is convex, then it's relatively easy to solve. You can just hit it with one of the convex optimization toolboxes, which are very efficient, and they're able to solve the optimization problem. But in this case, in these kinds of problems where g of x is neither convex nor concave, it's usually there are many tricks that you can use to solve these optimization problems. But before I talk about, here it is. The general approach is, one general approach one can use is what is called majorization minimization, and I'll explain that in the next slide. But here are some other examples of concave penalty functions that promote sparsity. So for example, g of x could be log of x squared plus epsilon, where epsilon is some small number. Again, the epsilon doesn't have a major role here. It only avoids singularities when x goes to 0. Or g of x equals log of mod x plus epsilon, or g of x equals x mod x raised to the power p, where p is between 0 and 1. So a general approach that one can use is called majorization minimization. I'll explain the basic idea through this graph here, and then I'll tell you some more details in the next slide. So suppose we want to minimize this function g of theta, which has this somewhat strange shape, and we want to find the minimum of g of theta with respect to theta, or what theta minimizes this g of theta. What you do is you start at some arbitrary point. In this case, it's marked as theta n minus 1. And you want to slowly move towards the global minimizer, which is somewhere to the left of the y-axis. What you do is at theta n minus 1, you construct a surrogate cost function f of theta. What is this f of theta? It is a function that you are sort of pulling out of a hat, and it satisfies two properties. One is that its value is equal to g of theta at theta n minus 1. So it meets g of theta at theta n minus 1. And it is an upper bound on g of theta for all other values of theta. So it sits above the graph of g of theta. Now, if f of theta, since f of theta is something that you are allowed to choose, you can as well choose an f of theta, which is easy for you to optimize. So for example, you can try to choose an f of theta, which is a quadratic function of theta. Then f of theta will be very easy to optimize because quadratic functions are easy to minimize. And then you minimize this f of theta. When you minimize this f of theta, you will go to some theta n. But because you've gone to the minimum of f of theta n will always be below f of theta n minus 1. But we know that f of theta is an upper bound on g of theta, and therefore g of theta n will also be less than or equal to g of theta n minus 1. So in other words, you've actually reduced the cost function g of theta by going from theta n minus 1 to theta n. Now at theta n, you construct another quadratic function, a new f of theta. And then you go to the minimizer of that cost function. And that minimizer will reduce f of theta by some amount. But because f of theta is always above g of theta, it will reduce g of theta to some value below g of theta n. And so on. So if you iterate this way, you can go from theta n minus 1 to theta n plus 1 and so on. After a number of iterations, you will converge to a minimizer of this function g of theta. You may converge to a local minimizer. That's a risk you have to always take when you're solving, when you're trying to solve these non-convex optimization problems. But at least you're guaranteed to approach a convenient point in the optimization. So this is the approach, the majorization minimization approach. What you do is to find an upper bound. In this case, the upper bound is denoted as f of x bar xm, meaning to say that this f of x is an upper bound at the current iterate, which is x of m. And it has this two properties. One is that it's an upper bound, and second is that f of x bar xm at x equals xm is the same as or is equal to g of xm. So it achieves equality at x equal to, this inequality is an equality at x equal to xm. Now this f of xm, x bar xm, is something that is convenient for optimization. So then you do this optimization. You solve for the x that minimizes this y minus phi x L2 norm squared plus lambda times the summation of f of mod xi bar xim. That gives you xm plus 1. Then you replace m plus 1 with m, and then you find a new upper bound at this new xm. And then you go back to step 1. So you iterate between this step 1 and step 2. Step 1 is to optimize the surrogate cost function f of x bar xm. Step 2 is to update f of x bar xm with a new upper bound. And as I mentioned, this works because g of xm plus 1 is an upper bound on f of x bar xm, so it's less than or equal to f of x bar xm is an upper bound on g of x, and so g of xm plus 1 is less than or equal to f of xm plus 1 bar xm. And f of xm plus 1 bar xm is the minimizer of f of x bar xm, so that is less than or equal to f of xm bar xm, which is equal to g of xm. And so g of xm plus 1 is less than or equal to g of xm. And so in each iteration, you're guaranteed to decrease this cost g of x. And so you're taking a step in the downward direction. And if your g of x has a finite lower bound, then this iteration is guaranteed to converge, or the cost function is guaranteed to converge after a number of iterations. This is a very effective approach. It can be used to solve all kinds of non-convex optimization problems. So in terms of optimization techniques, if there's one trick you want to take away from this tutorial, this is the trick. So I'll pause here and let you ask me if you have any questions, because this is a very useful trick to know.
Sir, I want to ask a question about, sir, if we do the supreme maximum value and minimum value, so what will be can we compute that, this equation, this Bayesian equation?
Sorry, say that again.
Sir, if we do the minimization and the maximization of the minimization, so can we compute this thing, this Bayesian rule?
But there is no maximization and minimization here.
Yes, sir, that is different. And so
there is no min-max problem here. It's only a minimization problem.
Okay, sir. Thank you, sir.
In this context, the min-max or max-min doesn't arise. It's only a minimization of the negative log of the posterior distribution Px given y.
Sir, yes, sir. Sir, sir, can you explain the from second step to third step? Can you explain the interpretation, sir? In this one, in this slide? No, sir. Previous slide only. Previous slide. Map estimation. Yes, sir. From second step to third step, can you explain the interpretation? How did we reach?
Yeah. So Py given x is the probability density function of y given x. So you know the value of x. I mean, that's how you think about it.
Sir, we impose the prior. We impose the prior. X means X. We impose the. Okay.
We impose a prior on x.
Okay.
This picture on the right is showing what is called a probabilistic graphical model, which is actually a dependence graph between x and y. So basically, this x1 to xn come from some random distribution. Okay, they're random variables drawn from the PDF P of x. And these give rise to your observations y1 through ym. Because y1 to ym are phi times x plus noise. So they're stochastically related.
Okay.
Now, coming back to step 2 to step 3, the first term is negative log py given x, but py given x, y is equal to phi times x plus noise. Okay, so if I'm given x, y is some known vector phi times x plus noise.
Okay, sir.
And if this noise is Gaussian, then y has a distribution which has a mean equal to phi x. The noise is usually assumed to have zero mean. So the mean of y will be just phi x.
Okay.
And
Okay,
the
sir.
covariance of y will be the same as the covariance of noise. And in this case, I have assumed the covariance of noise is the identity matrix. So then if I just write out the Gaussian PDF, then py given x is 1 over square root of 2 pi raised to the power m times e power minus y minus phi x transpose y minus phi x divided by 2.
Okay.
Y minus phi x transpose y minus phi x is nothing but the L2 norm of y minus phi x square.
Okay.
So if I
Okay.
just take the log of py given x, the 1 over square root of 2 pi power m is a constant. It doesn't depend on x. So I can throw that away. I don't need that term.
Okay.
And I'm
So
only
now,
left with the power in the part which is in the exponential, which is negative norm of y minus phi x square. But then there's a negative sign in the minus log part also. So the minus minus cancels. And I'm just left with y minus phi x norm square.
okay.
And
Okay.
this log p of x, I'm just calling that log p of x as g of x.
Okay.
This is some
Okay,
other
sir.
function. So for example, if p of x is equal to e power minus mod x, okay, it's actually p of x would be the product of e power minus mod xi. Okay, then log p of x will become summation of mod, negative log p of x will become summation of mod xi.
Okay, sir. Okay. Okay, sir. Now I understood.
Yeah. Then in that case, g of x is just g of x is equal to x in that case, or g of x is equal to mod x. But I could choose different. So basically, minus log p of x is g. And so when I say, for example, g of x is log of this thing, then this is equal to minus log of p of x. So p of x will become 1 over x squared plus epsilon, something like that.
Okay.
So I'm just saying, instead of telling you what p of x is and then taking its negative log and calling that g of x, I'm directly saying, okay, I'm going to choose g of x like this.
Okay. Okay, sir. Now I understood, sir. Thank you.
Yeah. Another sort of important point here is that we call it a prior, but it may not actually be a prior. We call it a prior to kind of develop a cost function that we want to minimize. And then we ask, what kind of g of x should we use to get the kind of solutions that we are after? So if I take 1 over x squared plus epsilon, that may or may not actually form a PDF. It'll only form a PDF if it integrates to 1, right? Otherwise, it won't form a PDF. But we even don't care about that part. We just say, let's just choose, we'll just choose this as our cost function and see what happens. Do we get sparse solutions? And if we get sparse solutions, we're happy with this cost function.
Sir,
These are sometimes called, these are sometimes called improper priors in the literature.
Okay. So this means we are just modeling p of x only. Just modeling p of x, sir.
Yeah, but what I'm saying is that this p of x need not be tied to any physical interpretation or meaning.
Okay.
We're just saying what kind of function p of x should I choose such that when I solve this optimization problem, I'll end up with sparse solutions.
Okay. Okay, sir. Thank you. Thank you very much.
Welcome.
Sir, this slide, sir, you just change it. So, sir, this slide, which one is the red one and which one is the blue one? In the log modex is the blue one.
Correct. It's not, I mean, it's not log mod x. Obviously, log mod x has a different shape. But suppose that was g of x.
Yes,
The
sir.
blue
Yes.
one. It had this
Yes.
weird shape and you wanted to minimize it. Actually, the final cost function that you want to minimize is not g of x. The cost function you want to minimize is this function here. It is norm of y minus px squared plus lambda times summation g of xi. So what is shown in blue here is somehow the combination of these two terms.
Okay,
Or
sir.
the effect of the combination of these two terms. That's what you want to minimize, that capital G of x. Okay, so yeah, this is where we were. So to continue, in particular, for example, if the function g of x is concave in x, then it turns out that any concave function of x, g of x, suppose it's any concave function of x, you can always upper bound it by the formula given here in the first line. That is, g of x is less than or equal to the derivative of g of x at xm. It's actually the gradient, okay, because x is a vector in our original problem. But if x was a scalar, then it would be the derivative at xm times x minus xm plus the value of g at xm. So I can form an upper bound like this. This is a linear function in x. Okay, so I can upper bound g of x. Any concave function in x can be upper bounded by the derivative at the current iterate times a linear function of x plus g of xn. Now my first term, now if you look at the last equation in this slide, you see what we want to solve for is this to minimize with respect to x of y minus phi x L2 norm squared plus lambda times the summation of this g prime at the current iterate xi of m times mod xi, because the cost function is now linear in x. And so this is a combination of a quadratic term and a linear term. And this is actually a weighted version of the L1 minimization problem that we saw earlier. And it can be solved just as easily as solving for the L1 minimizing, the L1 minimization problem. And so this is a convex optimization problem. It can be solved very easily using any convex optimization solver, or you can convert it into a linear program and solve it using a linear programming toolbox. And so basically this sub-problem is easy to solve. Once you solve this sub-problem, you will get xm plus 1. Then you compute g prime of xm plus 1. And then you update that and you again solve this weighted L1 minimization problem. So you can keep doing iterating between these two steps, optimizing and then updating g prime of xi of m until convergence. And this is called an iterative reweighted L1 minimization algorithm. And one nice thing about this approach is that because in each iteration, you're actually solving an L1 minimization problem, and L1 minimization itself is something that promotes sparsity, you will actually get sparse solutions in each iteration. And you can stop it at any time, and at that point, you will have a sparse solution. But if you run more iterations, you may get more and more sparse solutions if your g of x was more and more sparsity promoting. Now, if g of x was actually concave in x square, then what one can do is to consider a first order Taylor series expansion, which is what we did in the previous slide also. The right hand side here is actually a first order Taylor series expansion of g of x around the point xm. So you can do a first order Taylor series expansion around the point xm, but with it with the expansion done using x squared. So you take the derivative with respect to of g of x with respect to x squared, and then your error term will be x squared minus x0 squared plus g of x0. In this case, if you substitute for this upper bound in the original cost function, the sub problem that you need to solve turns out to be of this form. Xm plus 1 is the minimizer of y minus phi x L2 norm squared. So the first term is the same. That you're not touching. It's just a quadratic function in x. You like that function. That is easy to optimize. And the second term also turns out to be a quadratic function of x. In fact, you can write it in this form as another L2 norm squared term. And so the nice thing about this is that the overall function is simply a quadratic in x. And you can in fact find a closed form solution to this problem. So the solution is exactly what is written in the iterative reweighted L2 algorithm. First step, xm plus 1 is equal to wm times phi transpose times lambda I plus phi wm phi transpose inverse times y. So whereas here in the intermediate step also I had an optimization problem, so I cannot write a closed form solution to this optimization problem. I have to use a toolbox to solve it, whereas here I'm actually able to write out a closed form solution to this optimization problem. And so once I've solved this optimization problem, I have xm plus 1, and I have to take the derivative of g of x with respect to x squared and substitute the value x is equal to xm plus 1 to find the new weights wm. Then I can go back to the first step and recompute xm plus 2 and iterate between these two steps until convergence. So this class of algorithms is called iterative reweighted L2 algorithms. So for example, if g of x was log of mod x plus epsilon, then in the case of iterative reweighted L1, the weights turn out to be mod of xim plus epsilon inverse. In the case of iterative reweighted L2, the weights turn out to be equal to xim squared plus epsilon times mod of xim inverse. So you can actually work out what these weights are, and now you can see the weights are also a very simple form. So at the current iterate, you just calculate these g dash of xim or wim, and then you run the previous two algorithms. Unfortunately, even this is not the end of the story, because this maximum a posteriori probability estimation method, even though it works well, it turns out that this kind of concave plus convex cost function has many local minima, and so the algorithms have a fairly high chance at getting stuck at a local minimum, and so you may not arrive at the sparsest solution. And the other problems are more structural, in the sense that by construction, maximum a posteriori probability means that you're trying to maximize the posterior distribution of x. So it only guarantees that your posterior density is getting maximized. But it's not always the density that you want to worry about, but rather the probability mass, that is the posterior probability mass, rather than the peak or the mode of the posterior density function, that may be more relevant for continuous random variables. So for instance, maybe the posterior mean is a better estimate. And finally, the third point is that many times we are interested in the mean squared error in the recovered sparse vector, but map is a completely different criterion. It maximizes the posterior density. It says nothing about what the mean squared error in the recovered vector will be. So by design, they're not designed to minimize the mean squared error. So the mean squared error may be high. And in fact, what is interesting is that using the true statistics of the data often does not lead to the lowest mean squared error. That is, you can do a simple experiment where you generate your x according to a certain distribution, and then you ask whether you should use the same prior in the recovery algorithm or can you use a different prior? And it turns out for some problems, it's a different prior leads to lower mean squared error than the true prior that has generated your observations. So these are some of the limitations of MAP, in the sense that although the method works reasonably well in practice, it's hard to give guarantees, and your solution may get stuck at local minima. So to recap this particular section, we've looked at Bayesian estimation, in particular the basic map estimation problem. And we looked at the majorization minimization approach as one very general method for solving problems that can be written as the sum of concave plus convex cost functions. And we've looked at iterative reweighted algorithms, in particular iterative reweighted L1 and L2 algorithms. And we've briefly discussed about some limitations of these methods. See, I'm telling you these limitations in terms of, at this point, it's more you have to, it's something that you accept on faith. But in fact, in practical problems also, these limitations show up in terms of the performance of these algorithms. What would have been nice is if I had slides which show you the performance of these algorithms and show you where they're getting stuck at local minima and so on. But I don't have those in my slides, so you'll have to take this on faith that these map estimation algorithms, although in many scenarios, they outperform these previous methods that I discussed, like the L1 minimization or the greedy methods like orthogonal matching pursuit. They still fall short in terms of their performance in other problems. So that brings me to part 3 of the tutorial, which is actually the core part which I wanted to talk about, which is sparse Bayesian learning. I see that we are close to 1:30 already. So maybe we can stop here and restart at 2:30 if that's okay. Otherwise, we like to go on.
Yes, I will take break now and I will be back at 2:30.
Okay. So thank you very much for your time. I'm happy to take any questions. We still have 5 more minutes. Then we'll come back at 2:30 and start discussing about sparse Bayesian learning. By the way, I do have some of these tutorials available on YouTube and other places, and maybe also on my website. So if any of you have already seen some of these tutorials, then can you tell me so? Then I know that there are several people who already know this material, so I can maybe go a little faster in the second half. Okay, so I take it that for most of you, this is new material. So is the pace okay? Am I going too slow or am I going too fast, or is it okay?
Sir, it was a very nice presentation, sir. You, sir, can go this place. Thank you.
Okay. Say that a little louder, please.
It's new only, sir.
It's new, okay. Okay, very good. So if there are any questions, please ask. Otherwise, we'll meet again at 2:30. Okay, so we'll reconnect at 2:30.
Okay, thank you, sir.
Thank you.
Yeah, participants, we will be back at 2:30 over here. Have your lunch and then come back over here. Thank you all.
Yeah, so I'll stay signed in here, but I'm going to step away from my computer now.